Welcome to Unit 8, Lesson 1, Characteristics of Exponential Functions. So in this unit, we're looking at functions that are raised to a power of an exponent. And we need to start by understanding that there's some general functions that will tell you what to do with your base as well as your exponent in order to resolve the equation. So for example, if you have a function that says a to the power of m times a to the power of n, then to resolve it, you will have added together the two exponents a to the power of m plus n. So a represents whatever your base is. It could be like 2 to the power of 3 times 2 to the power of 4. So in your a to the m plus n, you'd have 3 plus 4, a 2 to the power of 3 plus 4. Keep this little chart on hand as you go through your unit. It will really help you to be able to solve the equations. An exponential function is a function of the form y is equal to c to the power of x, where c is a constant and c is greater than 0. And x is a variable. So the x is the exponent and it changes. We have two different types of functions. We either have increasing functions or decreasing functions. And you want to look at the behavior of the graph on the positive side of the x-axis. Is it going down or up? That will tell you whether it's decreasing or increasing. Notice that in the increasing functions, c is greater than 1. And in the decreasing functions, c is between 0 and 1, so it'll be a fraction or between 0 and 1. So our first graph, y is equal to 4 to the power of x. So the x is the thing that's changing. And there's a little chart here that shows you the mapping points for this function. Now, a common attribute of these graphs is that if there's no transformations to the function, if it's just y is equal to c to the power of x, they will always go through 0, 1. And that goes back to the other side where you have this general rule, a to the power of 0 equals 1. Anything to the power of 0 is always 1. So this point on your graph, you can look for that as a starting point, 0, 1, as long as there's no transformations done to the graph. It will always be in your base function. So we asked for some characteristics of this graph. Determine the domain and range. So the domain is x is an element of the reals. It's all numbers, negative infinity to positive infinity. I should mention that these graphs do typically have an asymptote. So you can see this one is extending off into negative infinity for the x values. It will never ever become 0 exactly. So in this graph, our horizontal asymptote is y equals 0. No matter how far to the left you go, you will never get exactly 0. There will always be a decimal there. This function has only positive values for y, so the range is y is greater than 0. It never intersects the x-axis, so there's no x-intercept. It crosses at y equals 1, which we already talked about. And then we call this graph increasing because it rises to the right on the positive x side. And the horizontal asymptote that we already discussed. In the second example, f of x is equal to 1/2 to the power of x, we get an example of our decreasing functions. You can see as it goes off into positive infinity, it's getting closer and closer to 0. And those values of x and those values of y are decreasing as you go to the right. So the characteristics of this graph, x is still an element of the reals, y is still greater than 0. So we have that asymptote at y equals 0. There's no x-intercept. The y-intercept is 1. And because it's decreasing, it's going down towards the right. And I just put a little note there. We already talked about it, but the question is, why do the graphs of these exponential functions have a y-intercept of 1? And it's because anything to the power of 0 equals 1. So those are the basic characteristics of these graphs, and you'll see this basic shape in all exponential graphs. You may also be asked to write a formula for these functions. And this can be a little bit trickier, but you just need to look for the pattern. So the graph is mapped here, but I included the table of values that goes with it. So what you want to see is when x changes by a value of 1, what happens to the value of the y? And in this graph, when we go up 1 x value, the y is decreasing by a factor of 4, or divided by 4. So we can get that value of c as 1/4 x, 1 over c. You can always plug in some points to see what's happening to the graph if they're not given and you're not given the table of values. You can just pick 2 points on the graph. -1,4 and -2,16 are really good ones, but you can also compare them to that base y-intercept of 0, 1. You'll see the same pattern there. The pattern will be consistent throughout all coordinates. It's not going to change. So once you know the factor, you'll be able to solve the equation. You can check to make sure that you're right by plugging in a value. So if you say we're using the point -2, so if we say y is equal to 16 and then we plug in that -2 where the x is, we should get 16 equals to 16, and that's how you know that your graph will be true. Sometimes you can be given application problems, so you'll be given a question, oh, you get sick with strep throat and the bacteria doubles every 10 minutes, or any example like that. It's really common in half-life of chemistry, of the elements, to see how long they exist in nature. So we use kind of 2 terms, but it's just another word for increasing or decreasing. We can either call it exponential growth. So think of it as like, oh, if I'm sick and I don't take medicine, my bacteria grow exponentially, or exponential decay, which would be applicable to the example that's coming up next. Typically, if you're given a chemistry example here, they'll use the word half-life, and that's the length of time for an unstable element to spontaneously decay to 1/2 of its original mass. So typically this is seen in radioactive elements like uranium or radium, which is coming up in the example. So it's just a term so that you know what we're talking about in the question. Here's our example. A radioactive sample of radium, Ra-225, has a half-life of 15 days. So what that means is every 15 days, it will be half the mass that it was before. The mass m in grams of the Ra remaining over time, t, is in 15-day intervals, and it can be shown by this exponential graph. So there's some questions on the right there. You can just read through them, but basically the mass of this sample that we're starting with is 1 gram, and we're looking at over time, if we leave it sitting, what will be the mass that's left over. Now, don't forget that each 1 increment represents a 15-day interval. So time 0, when we first put the sample out, it's 1 gram. If it's got a half-life of 15 days, that means 1 interval later, only half the mass will be left. So we go down from 1 down to 0.5 and carrying on from there. So you're just dividing the x value or the y value by 2. So it says from the graph, the m-intercept, that's just our y value, is 1. The initial mass of the sample is 1 gram. It's decreasing. So it approaches 0, but it never completely disappears. So from the graph, the domain is t is greater than or equal to 0. You can't have a negative time. And the range is between 0 and less than or equal to 1. So our maximum mass there is 1. And just like we talked about, the exponential decay model shows that the function looks like this. M as a function of time, the mass as a function of time, is equal to 1/2 to the power of the time. So the mass is decreasing by half every 15 days. Don't overthink it, just figure out where that mass goes. Part D is estimate how long it will take to decay the sample to 1/30th of its original weight. So you just can estimate 1 gram divided by 30 would give you 0.0333 infinity grams, or 0.03 grams. So you can just keep going along. You can either solve it algebraically and figure out what that value is, and then plug this mass into your equation for y and solve for the exponent. Or you can also just estimate it off the graph, see where does that 0.03 happen. Beyond this, you have some practice questions and you can complete those and then get going on your work.